All right, perfect. So yeah, if anyone in Zoom has any questions, then you can just type them in chat. We'll be able to see. And if any of you guys have questions also, you can just raise your hands or just speak out. So first, here's the link to the slides if you guys want to follow along on your own browsers. Give that a second. All right, so moving on, you can give a brief sort of intro to what exactly do we do in this workshop. So first, we're going to be teaching you the tools necessary for practicing technical interviews. So at the start of every workshop, we're going to be going over a sort of lecture portion. So the first sort of 45 minutes of the meeting is going to be giving new content, discussing topics and algorithms that you're going to be applying in the problems. So then the next part is going to be practicing using common interview problems in use for tech companies. So these are going to be just practice problems. And that's going to be another 45 minutes in every workshop. Then the last part is going to be actually doing the problems in an interview style. So we're going to be holding what we call mock interviews, where you'll be paired up with an officer and actually going over all of the problems in a sort of real environment where the interviewer is going to be asking you a question and you have to solve it live. So this is going to be starting next week when we start going over actual concepts and algorithms, as opposed to this week when we're just going to be overviewing and reviewing some stuff that should be baseline. So tentative schedule of what we're going to go over is the next workshop would be about graphs and trees. We're planning to hold an open office hours in week 4, where we'll just be going over like sort of any questions that anyone has. You can feel free to just drop by and talk with the team. In week 5, we'll be going over binary search. And then week 6 is dynamic programming. So now once all of this is done, the last 3 weeks are all going to be advanced topics, and we'd like to get your input in what you would like to learn in these. So we're going to have a feedback form at the end of the meeting, and please fill that out if there's any topics that aren't here that you'd really want to learn about. Now, moving on, a lot of the times people ask, what language should I code in the technical interview? And pretty much all companies will let you code in whatever language you're the most comfortable in. So most commonly, people use C++, Python, and Java. And in this workshop, we're going to be going over C++ since most people come in with the CS31 or CS32 experience, and that's the language that they go over in that class. So if you do want to use Python or Java, that's fine. You can ask them, our officer team. Most of us are familiar with the languages and we'll be able to help you out. So now for the start of the review. So does anyone know exactly what big O notation is? Anyone want to give it a shot?
Sure. It's the amount of times like a segment of code is ran. So if it's a for loop and there's like n items in a list, it runs n times. If it's a nested for loop, n squared, stuff like that.
Exactly. So yeah, that's a good way of going over time complexity. And like you just said, time complexity is the amount of time that the code runs, but in a format where we're actually caring about the scale of the problem. So as he said, in a for loop, if you run it with n amount of increments in the loop, whenever you change that n, you're going to be growing linearly, right? So it's going to be a linear time complexity. Does anyone know what space complexity is? And those of you in the Zoom, you can just type the answer in chat if you want to. That's close. So what space complexity really is the scale of space that you need to solve the problem. So not as much as how many variables you need to solve the problem, but if you're using any data structures that holds a collection of data, it's how big those data structures need to be. So suppose you're putting all of your elements into a list, right? And now if you have n items, the list needs to be of size n. So the amount of space that you're doing is going to scale linearly to the amount of inputs that you get, right? So now moving on, how to actually write big O notation. The format is O of complexity. Whenever you're writing big O notation, you always want to drop all the coefficients. So 5n becomes n, 250n squared becomes n squared. And now if we have a polynomial or something where there's more terms, you only want to keep the maximal term. So what does 3n cubed plus 5n squared plus n become? I'm sorry? N cubed, exactly. We would drop all of the coefficients, and since n cubed is a term that is the largest, we only keep that. Then our example is the list that we were talking about before. We have a list of n numbers. If we want to search through the list by checking every single element, that's going to be O of n complexity, since you have to go through the entire loop. Right? Now here's some review questions just for big O. So for the first question, assume we have a list of n numbers. What is the time complexity to generate all subsets of that list? And for those of you who don't know what a subset is, we have a list of, say, A, B, C, right? A valid subset would be just an empty list, or it could be just A, it could be A, B. Yeah, it would be 2 to the n. And the reason for this is every element can either be selected or not. So you have 2 options for every place. So you get 2 to the power of n. Right, so now for this example over here, what would be the time complexity to run this code? N squared. And now the reason for this is each of these loops happens n times, right? But since the inner loop happens as well n times, we actually have to run this whole thing. We run this count plus plus n squared times. All right, now what about this code on the right? Log n. Now, can you tell me what this algorithm is actually doing? Exactly. So this is called the binary search algorithm. And if you guys don't know what a binary search algorithm is, that's totally fine. We're going to be covering this in a later workshop. So the reason this is O log n time is because we see over here, every time that we perform this while loop, we cut our search space in half. And we terminate once we've found an element. So if we're cutting our space in half every time, it's going to be a log time. So now we get into just the data structure review part of this. So arrays and vectors, these are some of the bread and butter data types that you can be using in pretty much all your problems. And we have either a fixed size collection of elements, which is an array, or a variable size collection of elements, which is a vector. Right now, it's important to note whenever you put something in an array or vector, they all have to be of the same data type. So now a question for those of you who've used arrays and vectors before. When we have elements stored in an array, how are these contents actually stored in memory? So what is the representation of an array or a vector in memory on the machine? Exactly, it's a chunk of area, right? So what we call this is we call this a contiguous stored space, right? So what this means is if we have this array, this bottom array in this example, we always know that the 0 is next to the 1 in memory. And this allows us to do a lot of tricks with the actual memory locations of the array. And those of you from CS31 and CS32, you'll be familiar that the location of the element 0 plus 2 times the element size is going to point to this 2. So we can actually just directly reference the location of those memories. And that's what an array is doing when you give it an index. Right, that makes it really fast to access elements at any point in the array. So moving on to another data structure, we have linked lists. So now this is a data structure that stores a non-contiguously stored collection of elements. And what this means is in memory, we can have elements of the list be in any point. And now all we have are arrows that point to where the next location is. So over here on the top right, I've given an example of what a linked list struct might be for a single node in the linked list. Right? This would be a singly linked list because we have a node that contains some value and then a pointer to whatever the next node is that contains some value, right? Now, is anyone familiar with other variants of the linked list design? So does anyone know what other types of linked lists we could have? All right, perfect. So we have a doubly linked list. So now can you tell me what exactly a doubly linked list is?
Well, it's not like you have also pointer to the next element and the previous element.
Exactly. So you have two pointers. You have a pointer to the next element, but also you have a pointer to the previous element, right? And what this means is in this struct that we have for the singly linked list, we actually have to add another pointer. We have list node previous. All right. So is there any other variants that you guys are familiar with or any other changes to a simple singly linked list?
Sure. Could the tail node point back to the head node?
Exactly. Do you know what that's called?
I don't know.
That's called a circular linked list. What a circular linked list means is whenever we have a tail, so suppose this used to be the tail, we'll actually have it point back to the head. And this creates a cycle because we have everything going in a circle forever if we were ever to iterate through it. Right now, is there any other augmentations to the linked list that you guys have discussed before? So I'm gonna just go ahead and give it away. Something that makes a lot of problems a lot easier to work with is a dummy node. And what this means is, I'm gonna draw it a little bit bigger. If we have a head of a linked list, we actually are not gonna store any values in it. It's gonna be a dummy node that always just exists. Now the next point, it can have a value. And all of these have values until if we have like something like a circle, we come back to the dummy node and the head. And what this does is it really takes away a lot of the edge cases where a linked list has nothing in it. Because now we know that if we have a dummy node, we have a guarantee that there's always at least one node. And that helps a lot with some certain problems, as you'll see later. Now, the next data structure to talk about is a hash map. And this is simply a key value store of elements. So I would use this is if we had a hash map over here that contained some sort of key value store, if we query it for 2, it would return an apple. If we query it for 6, it would return a pear. If we query it for -3, it would get an orange. Right. And now, is everyone clear about all of these data structures? Is there any questions? All right, nothing in chat, so we can move on. All right. So this is a very useful slide. It details all of the time complexity for operations in every data structure. So this is something that's very good to know when you're actually going to an interview. So whenever you use one of these data structures, you'll always be able to tell the interviewer what the time complexity of the operations that you're writing are. So for now, you can just refer to this chart, but it's very good to just sort of memorize exactly how this works and what caused it to be the time complexity. So is there any questions about time complexity of operations? All right, nothing, so we can move on. So we can actually get straight to practice problems. So today's, again, as I mentioned at the start, going to be a little bit different. We're not going to be having any mock interviews, and instead we're going to have 2 sets of practice problems. The first set are going to be what are called ad hoc problems, or just problems that don't neatly fit into any other category. So what this means is we'll be teaching you a lot of tips and tricks to just look at a completely unfamiliar problem and sort of approach it and get to the solution. And then the second set of problems are going to be problems that have to do with all of the data structures that we've reviewed. So they're going to be problems that have to do with arrays, linked lists, vectors, and hash maps. So to get us started off, Suhas has a problem that he's shown.
Thank you, Neil.
Go ahead.
Right. So before I get into the problem, I think it's just worth highlighting just a few differences between an interview and, say, something like a programming competition. So the first and foremost thing that I want you guys to keep in mind is to separate the problem from the computer. Whenever you're trying to think about the solution to a problem, especially in an interview context, it's really easy to say like, oh, I'll use a for loop to do this, and then I'll store it into a variable. But oftentimes we want to think more abstractly. We want to describe our algorithm in terms of like how it actually works, not how we would code it. And so I want to practice just like seeing an unfamiliar problem, kind of separating it from like the coding representation of it, and just looking at how we would solve it. So here are the steps that you would want to practice in a technical interview. Notice that there are quite a few steps that happen before we even get to writing any working code. That's only step 5. There are quite a few other steps that we want to get through. So first and foremost, we want to repeat the question in our own words. Oftentimes it helps to just boil down the problem, pick out the things that we really care about so that we know what to focus on. It's just like how you would solve any math problem in any exam, but it also applies in an interview. Next, and this is probably one of the most important ones, is check assumptions and ask clarifying questions. Oftentimes, the problems that interviewers give us are going to be incredibly vague, and that's often done so purposely. It's on you, the person actually taking the interviewer, to ask your interviewer for constraints. Ask your interviewer for things that you don't want to assume. Is the array sorted? Is it not sorted? That can oftentimes change the algorithm that we want to apply. So we definitely want to check those assumptions and ask those clarifying questions. Next up is using real examples. Oftentimes, interviewers just want to hear your thought process, right? And what's the easiest way to start in a problem? Try a value, try a test case yourself, walk through how it works. That not only helps your interviewer, but it also helps you think. Because if I were to just give you a problem, it takes you time to think of the solution. And you don't want to just be sitting in front of your interviewer for 5 minutes in silence, right? You want to at least be making some progress towards the solution of the problem. And oftentimes using an example is the best way to do both. Finally, you want to brainstorm solutions and their time-space complexity. Now, generally speaking, a neat little trick is that if no time or space complexity is specified, you can oftentimes just like start at the slowest one and optimize it. It can look cool in front of your interviewer. But oftentimes you want to eventually arrive at the fastest solution. And then finally, in the 5th and 6th step is where you write your actual working code, and then you test the code itself. So we've gone through the 6 different steps, and I want you guys to apply it on the next problem. So, specially sorted search. So given an n by n matrix, where the rows and columns are individually sorted in increasing order, determine if an element exists in the matrix. So for starters, if we go back to what step 1 is, repeating the question in your own words. I kind of have made it easy, but if we were to pick out the important details in this question, what would it be?
Individually sorted, increasing order.
Yep, this is definitely important. And can we see that actually in the matrix? Like, what does that mean in terms of the matrix that's been provided?
Means you can kind of split into grades. So if you search for, this is working with 26. Let's say on the top row, you can just search until you get to a number that's larger than 26 and then go back 1. And then you only search that one column.
Exactly. So we have the fact that it's individually sorted, which means that our rows are sorted in increasing order. So for example, our first row is 10, 20, 30, 40, 50. Our second row is 15, 26, 33, 44, 55. All of those are sorted in ascending order. And the same can also be said about our columns. And you provided an interesting approach about going through row by row. We'll talk about that after, but before we get into the solution, I know it seems a little like, why are we doing this? We're just going really slow, even though we can just skip past. But I really just want to make sure this process is kind of nailed down. So we've kind of picked apart the important details in this problem, which is mainly just the fact that it's individually sorted. And now we want to check our assumptions and ask clarifying questions. So this problem is intentionally vague. So what are some things that come to mind that are not listed in the problem but might be helpful to know? Well, first of all, I see this. What does this mean in a vacuum? N by N doesn't really mean much in a vacuum. It doesn't point me towards like how fast of a solution am I going to need? Is it like this big of a matrix with a single element inside? Or is it a huge matrix where I might actually need a very optimal algorithm? So stemming from that, one important question that we want to definitely determine is the size of what N is. What's another question that we might be thinking of? In searching algorithms, there's two cases that we always want to consider. What are the two cases we always want to consider in any searching algorithm? Well, what are we trying to do, first of all? Find an element. But what if that element doesn't exist? So that's another question that we might want to ask is, do we need to handle the case where the element doesn't exist? Because that can change the algorithm as well. Like for any searching algorithm, knowing whether it exists or not is important. So that's just an example of some assumptions and clarifying questions that we want to check. Next, we want to do just a basic example and search for an element. So what is the most basic version of a search algorithm that we can think of? Something that doesn't use anything fancy, is just the most basic way of sorting or searching for an element in a matrix. Just check all of them, exactly. So we can kind of see this process laid out where the straightforward approach is to search through every row of the matrix linearly until the element is found. If it isn't found, the matrix does not contain the search element. What does this look like? Well, we search at 10, it's not there. We search 20, it's not there. We keep repeating this process over and over again until finally we hit 26. And then we see that 26 does exist in the array. And so we know it's there. So first of all, what is the time complexity of this algorithm? And oftentimes the time complexity, yes, we could have found the element right here. But what we want to do is consider the worst case scenario. N squared, exactly. Worst case scenario, the element we wanted to find was 100 or it didn't even exist. And so we had to go through every single row and every single column. Now, from this straightforward approach, it's probably apparent that that's not the intended solution, right? It's likely that there's something cleaner involved. And the way that we can figure this out is by asking ourselves the question, is there any information we did not use from the problem statement? While it is true that sometimes problems try to throw red herrings at you, information that isn't necessarily relevant, there is a good chance that most of the information in a problem is going to be relevant to the solution. So what is the answer to this question? Is there any information that we did not use from the problem statement? Sorted. Not just the fact that the rows are sorted, but also the fact that the columns are sorted. So what we want to do is we want to go back into our problem and think of a way to do this. Now I'm going to open the floor to you guys to just think amongst yourselves or just throw out any ideas. If you've already seen the solution, then maybe try and hold it to yourself before shouting it out. But do we see any kinds of just starting points to start our solution off at? There are no wrong answers, by the way. Binary search, that is a great idea. So if we were to try and binary search, we could go row by row and binary search for the element in this row. Go to the next row, binary search. Oh, look, we found 26. That's great. What is the time complexity of that algorithm? N log n, exactly. And so once again, though, I will throw back the question. Is there any information we did not use from the problem statement in that binary search solution? It is a perfectly valid solution. And that is a great thing to bring up in an interview, the fact that there is a more optimal way to do it. But is there any information that we didn't use?
Sorted column-wise too.
It is sorted column-wise. So while that is definitely a right solution, it's possible we can maybe get it faster. So I will say that we can get it faster, but do you guys think of any other way to get it. So if it's not n log n, this is another neat trick. Like if we think that we can get it faster than n log n, what is the algorithm probably going to be in terms of time complexity?
log n
It could be log n,
or n.
probably n first before we get into log n. So if we're trying to think of an O of n solution to this problem, we want to think of a solution that maybe just like only has to go through the rows once and through the columns once. And so an idea that comes to head is some kind of traversal, right? We start at the element 10 and somehow we navigate our way through this array until we find the element that we're looking for, right? But there is a small issue with that, which is that if we start at the element 10, how do I know if I want to go to 20 or if I want to go to 15, right? I want some kind of path where I can always know to choose a right or a down and just make a path to the element I want to find. But it's unclear whether I should go down the route of 20 or if I should go down the route of 15. There's two options that look equally as promising to have the right value that I want to find. But that's assuming we start at 10. Can we think of this approach starting at a different value that isn't necessarily 10? I know that's left purposely vague, but I do want you guys to think about it. The issue with 10 is that if we're looking for 26, we don't know if we should go right or down, right? It's sorted, but both of those elements are larger. 26 is larger. I could go down either road. But that's assuming I start at 10. All right, I got something in the chat. Someone said 38. So if I start at the middle, the caveat here is that, if I start at the middle, it's close because like, yes, there is a way I could go down and there's a way I could go up, but there's also 4 different directions I can take. So if I start at 38 and I want to find 26, which is smaller than 38, do I go left? Do I go to 30? Do I go up to 33? It's unclear where I should go from there. So it might not be 38 because there's 4 different directions we can take. But what spot has a lot less than 4 directions we can take? Let's try and narrow down where we want to start. Any ideas as to what narrows down the amount of directions we can take?
Any of the corners only have 2, and the edges have 3.
Exactly. Corners have only 2 directions that they might want to take, and edges have 3. So let's start off at the corners. We established that 10 probably won't work, right? There's 2 different routes I could take. It's unclear how I should decide between each one. So maybe not 10. But what about something like 50? Well, 50 is a little bit special, actually, because 50, if we look at the 2 directions that we want to take, it actually is a little clear which direction we want to go. And why is that? Well, if we look to the left of 50, there are only numbers smaller than 50 to the left of it, right? Because it's sorted in increasing order. And if we look below 50, there's only elements larger than it. So depending on where this element falls relative to that, we know what direction we have to move. So let's take a look at how this might play out. So we start at the top right corner of the matrix. If the desired number is smaller than what we want, we move a column to the left. And if the desired number is larger than what we want, we move 1 row down. So we start at 50, and we see that 50 is not our element. 50, or actually, let me do it this way. 26 is less than 50. So we know it is going to be found somewhere in this submatrix, right? There's no way that 26 will be found anywhere here. So what do we want to do? We should just move 1 column to the left. And that brings us over to 40. Now, once again, 26 is less than 40. And remember, we've already crossed out that these guys cannot be 26. But now, because we know that 26 is less than 40, we know that 26 must lie somewhere in here. And so we can cross out these guys from also being where 26 is going to be, because all of those are greater than 40, and we know 26 is less than 40. We repeat the process again. 30 is greater than 26. And so we end up crossing out all of these because we know 26 has to be here. Now, 20 is a little more interesting. 20 is actually less than 26. That means that we had already crossed out here, but now we know that 26 cannot be in any of these two elements. So we know that 26 has to be here. And notice that as we narrow that search space down more and more, we end up finding the value that we wanted to find, which is 26. And we can see that the time complexity here is O of n, because the worst case scenario is that we go all the way to the left and all the way down. And even then, that's just going to be O of 2n. And we talked about how proportional or the constant doesn't matter in front of the n. So that just becomes O of n. And this is a clean and fast way to arrive at the solution. But once again, this was less about the actual problem itself, but more about how we apply different approaches to solving the technical problems. We want to start at the most broad solution, whittle our way down. We want to make sure we're always checking our assumptions, asking clarifying questions, just making sure we buy. I know it sounds weird to say stall and like buy time, but essentially that's kind of what you're doing. You're trying to get time to think for yourself, to come up with the most efficient solution. And in the end, even if you don't end up coming up with it, at least you have demonstrated your ability to problem solve by doing these first 4 steps. So sometimes it doesn't even matter that you miss the most efficient solution. What they wanted to see is your thought process, to see if you think like a programmer. And by applying these 6 steps, that's effectively what you're demonstrating. So with that, is there a cleaner way to do it? Oh my gosh, that is so much better. Okay, with that, I'm going to hand it off. Yeah.
Hello, everybody. So let's just step through this approach with another problem, magic triplets. So let's call a triplet of natural numbers, ABC magic, if A divides B and B divides C. So we are given an array L of natural numbers, and we are looking for triplets where ABC are elements of the array with sequential indices. So there are 2 example inputs. So we know that for list 1, 2, 3, 4, 5, 6, we get output 3, and for list 1 to 3, output 0. So let's just step through that algorithm of approaching an interview. So step 2, asking questions. So what kind of questions immediately come into mind when you read this kind of problem? So basically, from example input, we see that both examples have sorted arrays, and it could be not clear if the array is sorted or not. So it's a good idea to ask, and the answer is no, array is not always sorted. So another question you could ask is, can numbers be equal, since in all examples numbers are distant? Yes, numbers can be equal. So the idea behind this is that you should always, whenever you have some uncertainty about the problem statement or example input or output, you should always ask questions. It's better to ask a simple question, maybe not too complicated, but it's better than just assume and something and solve a wrong problem. So, well, kind of similar to the previous problem, we also want to know the constraints. So it's basically questions about constraints are the most common. We should meet. Sorry. So basically, questions about constraints are one of the most common in the technical interviews, and anytime you need to approach a problem, it's a good idea to ask about constraints. And can anybody think of any other questions about the problem statement or the problem overall? So maybe not very obvious question, but sometimes it's good to ask what kind of result we are expecting. So what if our result is greater than the limit for the type we are going to use? For example, if we are dealing with numbers with many digits, then we'll probably use strings to store them instead of integers. So for this problem, it's kind of clear that if we only have n numbers in the list, then there is a limited number of triplets and it falls within the range of ints. However, it's just a good question to keep in mind that sometimes the constraints for the result can be unexpected. Okay, so moving on to the next step. We are given 2 examples, but we never really looked what's going on there. So let's look into that. So for example 1, we have 6 numbers, 1, 2, 3, 4, 5, 6, and the triplets that can be built from this list is 1 to 4, since 1 divides 2 and 2 divides 4, 1 to 6, since 1 divides 2 and 2 divides 6, and 1 to 3, 1, 3, 6, since 1 divides 3 and 3 divides 6. And there are no more other triplets that are magic in this list. And that's why the result is 3. And for example 2, there's only one triplet possible with sequential indices, and it's 1 to 3. And since 2 does not divide 3, our result is 0. There are no magic triples. It's always a good idea also to step through your own examples. So basically, you can propose a list, an array of numbers, and try to see what would be the output for that array. It helps to better understand the problem, and also when you finally come up with the code, you can plug that in and check if it's working correctly. But for the sake of time, we'll not do that now. So let's move on to the next step. So the easiest approach that you can take is to check every single triplet. And that's probably what we did when we stepped through the first example. We checked 1, 2, 3. No, it's not right. 1, 2, 4. Oh, it's a magic triple. Then we at least have 1, and so on and so forth. So that's something that's going on here. We have 3 nested loops, and for each 3 elements in the array, we check if the first divides second and second divides third in order, and increment our result variable if it does. So basically, let's step through it. So first we check is 3, 6, 2 magic? No, it's not. Then if 3, 6, 4 magic? No. If 3, 6, 36 magic? Yeah, it is. So we add 1 to result, and so on. So can anybody think of what time complexity will this algorithm have? This code on the right.
That a
Yes, it's n cubed. We have 3 nested loops, and for each one we are looking in the range of order of n. Therefore, the time complexity is n cubed. It's worth to mention that whenever you get time complexity of n cubed or even n squared, or this kind of time complexities, it's a sign that you probably did something wrong. You should probably look into more efficient solution. So do we really, yes, so time complexity is n cubed and it's too slow. So do we really need 3 nested loops? Well, the answer is no. We can devise a better solution. So let's look closer to what's going on in the array. So we have a triplet A, B, C, and basically every element of the array at some point can become A, can become B, or can become C. And it's worth to mention that they follow this. So A divides B, and B divides C. And so it's kind of intuitive that B is kind of the most important number here. So let's just look at our array. And suppose element X is B for our triplet. So basically the middle number. Then we know that we choose one number from the first part, which is the first number for the triplet, and we choose one number from the second part of the array, which is the third number for the triplet. And they all should follow these two constraints. Something to notice is that these two numbers, A and C, are basically independent. As long as A divides B and B divides C, we have a magic triple. So here's an idea. If we could knew that in the first part of the array there are, let's say, K1 elements that divide it. So there are K1 possibilities to choose an element from first part of the array that divides B, divides X. And there are K2 numbers from the second part of the array that B divides. That basically means that we can choose any number from the first part, we can choose X, and then any number from the second part and get a magic triple. So there are K1 possibilities for the first part, K2 for the second part, and we can easily devise how many magic triples in total we can get. So with this in mind, let's consider the following algorithm. So instead of 3 nested loops, we'll only look at every pair in the array. So every time you find a pair, Ly and Ly, where the first element divides the second one and their indices are sequential, then we'll increment next for the first element and pref for the second element. So what are these two arrays? So we'll use array pref to store the number of elements for each entry. We will store the number of elements that go before that element and divide it. So basically, we will store our number K1. K1 goes here. And for each element of the array, we'll also store value in the array next. And basically, that will be K2, the number of elements that go after that element in the array that this element divides. Okay, so it's probably hard to see what's going on from the first glance. So let's step through it with an example. So we will just take an example from the task, but you definitely can choose your own example, as I said. So we have this array 1, 2, 3, 4, 5, 6, and we will just step through this code on the right. So the first pair we compare is 1, 2. 1 divides 2. Therefore, we increment value for pref for the second element, since there is one element going before it that divides it. And we'll increment value for next. for the first element, since there is one element that goes after one, that one divides. Okay, so the next step, we compare 1 and 3. Sorry, not compare, we consider 1 and 3. 1 divides 3. Again, we get that there are two elements that go after element 1 that 1 divides. And for each element, 2 and 3, there is one element that goes before it that divides it. Okay, and so on and so forth. So when we step through the inner loop for element 1, so we compare, we consider 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. We get something like this, since 1 divides every single element, and then every single element divides 1. So we get the 5 elements that go after 1 can be divided by it. And there's just one element before every other element that 1 divides. Okay, so, and we continue this comparing, considering 2 and 3, 2 and 4, and so on. So finally, this is what we get. So what this basically means, so I'll just give one last example. So for this element here, which corresponds to number 4, there are 2 elements that go before it in the array, in the original array, that divide it. So, well, once we get it, what does it actually mean? So, does it have any particular meaning in it? So, for example, for this element, what does it mean that it has pref number 1 and next number 2? Can anybody suggest what these numbers mean?
I think you just multiply those two together and add it to a counter, and that should be the number you have.
Exactly. Yes. So basically, there is one variant to put an element for the first position in a triple. We put so the original element is, I think it's 2, so it's here, and there are 2 possibilities for the third element. So basically, there are in total 2.1, 2 multiplied by 1, 2 possibilities for magic triples, where the middle element is the element that we consider in the array. So with that in mind, here is the full solution for the problem. So basically, the first part is initialization of the variables. Then the second part is stepping through every pair and checking if the first element divides the second one. And finally, once we get the values for every single element, for the number of triplets that can be devised where it's the middle one, we simply add these values to the result and return it. So now, can anybody think what the time complexity for this algorithm is? Yes, it's n squared, which is still not what we might expect, but this is better than n cubed. And it's always good to question yourself, is this the most efficient algorithm I could come up with? Okay, so that's almost it from me. Do anybody have any questions about this problem? Okay, then I have one question. So what is the space complexity for the first and second algorithms? So for example, for the second one, what is the space complexity? Sorry? Yes, O(n). And can you explain why?
The 2 vectors that you created.
Yes, so we created 2 vectors of size, each of size n, so the space complexity is of n. And how about the first algorithm? Oh, actually, no. About the first algorithm?
Oh, one.
Yes, so we don't create any additional vectors. We only use single variable result. Therefore, the space complexity, interestingly, is better for the first algorithm than the second one. So, oh, I'm sorry. So another idea for a question that you might ask your interviewer is, what are you looking for? Are you looking for the best space complexity or are you looking for the best time complexity? Okay, now that's all from me. Thank you. And yeah, I hand it over to Neil.
Yeah, so we'll be getting into one more ad hoc problem in just a second. So does anyone have any questions about any topics covered so far, any of the data structures, anything that we've done so far in this workshop? Otherwise, we can take a 5-minute break and come back in just a bit. Yeah, also, if you have any questions during the break, you can just drop it in chat if you're in Zoom. That's perfectly fine. unmute.
Oh, okay. Oh, okay. So now we have this problem exam. Wait, also, am I supposed to give them time to look at the questions?
Yeah.
Okay,
You can actually see it.
wait. Be on
Sit
this
here
side?
and then
Okay.
draw that.
So, please look at this question for a little bit. I'll read it. I guess you can read it, but basically you have like, you're given like two strings as the input, and then you're trying to find the maximum number of correct answers that you got on an exam. So the two strings are like your answers versus your friend's answers, and you also know that your friend got like a certain number correct. And based on that information, you want to find the maximum number of answers that you got correct. So to get a better understanding of what this problem is saying, you can take a look at the sample input and output. So I think the first one is pretty short and kind of intuitive to understand. Basically, the first line, 3, it's telling you that your friend got 3 answers correct on the exam. The second line is the string containing your solutions. And the third line is the string containing your friend's solutions. So your friend got 3 correct, and the maximum possible number that you got correct is 2. And the same thing applies to the second sample input and output. It's a little bit longer, but I will walk through that input output combination in my next few slides. So does anyone have any intuition about how to approach this problem? Thank you. Okay, so I will introduce one of the approaches that I use. So we know that we're given 2 strings and that we have to do some sort of comparison between your answers and your friend's answers. So the strategy is to iterate through each answer one by one, compare your answer with your friend's answer. And for each problem, there are 2 cases. Either 1, you and your friend got different answers on the problem, or 2, you and your friend got the same answer on the problem. So now what do we do in these 2 cases? Since our goal is to find the maximum possible score that you got, we want to assume the best case scenario. And so when you and your friend get different answers, you want to assume that you want to assume that you are correct and your friend is incorrect. On the other hand, if you got the same answer, then you can assume that both you and your friend are correct. However, we can't just keep like making the assumption for every single answer, right? Because then you would just say that, oh, the maximum score you got is the perfect score. Because the number of assumptions you can make is limited by the actual number of answers your friend got correct or incorrect. So as a result, while you iterate over the answers, it is important that we count the number of assumptions that we make and keep track of how many remaining possible correct and incorrect answers that your friend can still have. And so to illustrate this, I will walk through the second sample input output that we saw earlier. So here we have this sample input output, and we know that each string has 10 letters. So we have a total of 10 problems / answers, and we're given that your friend got 6 problems correct, or 6 answers correct, right? So then we know that by simple subtraction, he got 4 incorrect answers. And let's just iterate through the string 1 letter at a time. So first, take a look at the first letter. Both of you got like T, which is true, I guess. And here we can make an assumption that you are correct and that your friend is also correct. And now, after we make this assumption, we increment the maximum possible of correct possible number of correct answers. And we consider the remaining problems on the exam. So out of the remaining 9 answers, right, we already made one assumption about the previous one. So we kind of decrement the number of possible correct answers. So out of the remaining 9 answers, your friend can still have 5 correct answers and 4 incorrect answers. Initially, it was 6 and 4, right? So we go to the second letter, and again, you got the same answer. So we do the same thing, increment maximum possible count, and then out of the remaining 8 answers, your friend can have 4 correct answers and 4 incorrect answers. And now, on the third letter, we see that you and your friend got different answers. And once again, we're able to assume the best case scenario where you are correct and your friend is incorrect. Because on the right-hand side, we say that there are some correct and incorrect answers remaining. So here, we make the best assumption and we consider, again, the remaining 7 answers. Your friend can still have 4 correct answers and 3 incorrect answers. So we just keep doing this for like the next few letters. And here, look at the 7th letter. So at this point, right, we have 3 remaining answers, and notice that we already assumed 6 times that your friend is correct. And this implies that we can no longer assume for the future answers that your friend is correct. So for the remaining 3 letters, we can only assume that your friend is incorrect. And we'll increment our final answer count based on this. So again, at the 8th letter, there are different answers, and you can assume that you're correct and your friend is incorrect. Now, at the 9th letter, right, remember that we already assumed that your friend is correct 6 times. We can't do that anymore. And so here we will just kind of like, I guess like your friend will just take the L and then he is incorrect. So now we can only assume your friend is incorrect. And because you guys got the same answer, it implies that you're also incorrect. And then, we go to the last letter. And you got the different answer again. And because you're allowed to, so before this, your friend has 1 possible incorrect answer remaining. So we can just assume that is the case, that your friend is incorrect and you're correct. So at the very end, you'll find that the answer is 9. And so we will return that as the answer. And here is the example solution code for this. Does anyone have questions about how we approach that problem?
Okay, I guess we'll solve another question, because this is why we're here, right? A maze. Okay, so this question is basically we're given a rectangle of a set width, and we're given a set of rectangles of fixed size, but so what we're trying to do is we're trying to have the set of given rectangles into our big rectangle, and then we want to output the final width and height. So this question is pretty easy if you think, if you just look at the illustration. So basically, say if this length is our given width limit, what we can do is we can just keep putting the rectangles in until that if we add one more little rectangle inside, it'll exceed our width limit, right? in which case we'll have to put it on the next row. And then our next row begins, because we don't want to clash with all the rectangles that we have inside. So what we want to do is we want to find the max height of our row. And then we want to put one below that. Does that sort of make sense? I'm gonna assume this is a good silence. So yes. Okay, so what we can do is we're just gonna do what we said. So then we're given a set of rectangles, right? And a width limit. So what we can do is we can traverse through all the rectangles and then we can hold, we can have 4 variables. The first 2, we can keep track of our current row's width as well as our max height, right? And then when our current row's width is almost greater than when like our current row's width plus our current rectangle that we're looking at exceeds the limit, then we know that this is currently our width. We just like create a new row, right? So we save our max height and then we move on to the next row. And then we repeat until we looked at every little rectangle. Yes? Yes. Pretty simple question, right? Yes, amazing. Okay, so this is basically the pseudocode for that. Amazing, pretty easy. So yes, and then one thing to, I guess, to sort of look at is the negative ones. You might wonder why they're there. They're there because that is in the problem statement. So that's the terminal condition. That's why it's there. So if we're given 2 negative ones, that means that that is the end of the input. So we don't think, we don't look at the rectangles anymore because -1 width and height is invalid. Amazing. Okay, now let's move on to your favorite data structure problem.
So first of all, before we go over the more conventional data structure problems, does anyone have any questions about the ad hoc problems that we just went over? All right, if everyone's good, then we'll get started on a data structure review problem. So these are going to be ordered from easiest to hardest. So we're going to start off with a couple of simple data structure problems and then work our way up to harder problems that require some combinations of data structures. So first of all, we have the single number problem here, right? And the problem statement is basically we're given an input where every element in the array appears twice except for one that appears once. Right, and it's pretty clear in this input that we see that the 1s are matched together, the 3s are matched together, and the 4 is the odd one out. Right, so our problem is to look at this array and output the 4. So does anyone have any ideas how we would go through solving this problem? Like, at a first glance, what is a way to approach this?
Python dictionary or hash table.
A dictionary or hash table, that's a great idea. So anyone here want to explain exactly what a dictionary is?
Honestly, I don't know. Honestly, I don't know what it is. It's just what the Python dictionary is, like Python hash table is.
Okay, so how a Python dictionary works, right, is we have an arbitrary key value store, right? We talked about what a hash map is, where we index it using some sort of key. So suppose that this has A in it. We point it towards a value, right? That's what a hash map is. So what the suggestion here is we know that since every element appears 2 times except for 1, we can actually put this all into a hash map that looks like this, right? When we're going through 1, 1, 3, 4, 3, what would a hash map look like if we're going to keep adding numbers that have appeared, right? So we start off with a key value store that's empty. Now, what would we do at the first point when we hit this 1?
arbitrary value. Just, I think you just need to store the fact that you like encountered a number already.
The fact that you've encountered a number already. So are you suggesting we'd put like a true, as in we've seen
Like
this?
a Boolean.
Okay, so we can definitely do that. So we have a key that's 1, and we map that to the fact that we've seen it. Right? So now, as soon as we hit the second one, what do we do with this value?
And this is just move on to the next number. 'Cause
Move on to the,
that's-
okay. So let's take this idea and see what happens, right? We'll move on to the next number, just skip it. So now what happens when we hit this 3, right? We're gonna say we've seen the 3. Like, is it true?
Oh, never mind. I'm
Right, we
sorry.
see the
Hold
4.
on.
That's fine. We'll explain why it's wrong and then get to how to explain, right? So the idea of just putting whether or not an element exists, it's a good first step, but the problem here is we don't have any way to differentiate between something we've seen twice and something we've seen once, right? If we only know that an element exists, we're missing that crucial point of information. So what would the addendum be? How would we deal with this?
Initially set it to 1 when you first encounter it. And then when you find another one, make it 2.
Yep, that's a great idea. So now, a better way to do it that would actually give us that information of how many times we've seen it is just keep a running count of how many times we've seen it. So when we first encounter a 1, we put it as a 1. Now, when we see it the second time, we actually change the value and update the value in the mapping to a 2. So what this allows us to do is when we see the 3, we give it a 1, we get a 4, we give it a 1, and now when we see this 3 for the last point in time, we give it a 2. Now the solution is pretty clear what we do in this next step, because all we have to do is search through the entire key space and figure out which one has a value of 1. Right, is that solution clear? Does everyone get how that actually works? Okay, so now the question is, what is the time complexity here? How much time does this take? O of n? Exactly. So this is going to be a time complexity of O of n because we take one search through the list and then one search through them. And the reason these are both O of n is because the maximal size of this hash table is actually n over 2, right? Because we know that every element either appears once or twice. So when we have a bunch of numbers, you have n over 2 of those numbers in the hash map, right? Now, when we talked before about big O, we say that we remove the coefficient. So we remove that 1/2 to just say n. Right, so the time is indeed O of n. There's one more way to measure the algorithm, and that's space complexity. So how much space complexity would we have in this solution?
Why is that?
Anyone want to explain why this is an O of n space?
Because the only variable created is the hash table. And that is like based on at max this n. Or no, just n.
N over 2, that's
Oh,
correct,
okay,
yeah.
okay.
So there's an important distinction to make here, and this is really confusing for a lot of people. Space complexity isn't the amount of variables you create, right? You can fixed size create like 100 hash maps, right? And that's still constant space because it's still a variable you're creating. We want to know how big the actual hash maps are, right? So when we're creating this hash map, the space complexity is defined by how many elements we put into this hash map. If we have a hash map that always has a finite mapping of 1, right? That's still constant space complexity because we know exactly how much we're allocating. And it's independent of the input. So we have an O of n space complexity. Now, this is a great solution because when we're given a list and we don't know anything else about that list, like if it's sorted or not, usually the fastest time we can get when we're worried about like elements in the list is O of n because we have to search through the list to get some sort of condition, right? So that should indicate that this time complexity is good. But is there anything we can do about the space complexity here? We do want to reduce it.
I think maybe if there's like only one or two pattern repetitions, you can just make it a Boolean one hash map.
That's true. So the suggestion here, right, is change it from an int to a bool, right? Now this is a good idea, but also doesn't completely solve the problem, right? The logic here is we know that an int is going to take 4 bytes of space.
We can actually just delete it.
You delete it completely.
I mean, if we counter the same item twice, just delete it.
Exactly. So that is a hash set, what they're talking about. So now instead of having a key and value, the key is the value, right? So we have 1, right? We have the 1 canceled out by the second one. We have the 3, the 4, and we remove the 3, right? Now, this does reduce the physical space needed, but why is this still not better in space complexity?
Theoretically, at some point in time, you could have a full.
Perfect. So consider this. What if we had something that said 1, 3, 4, and then 3 and 1? In this pattern, we would actually fill up the hash set completely, right? Thus, the maximum size of the hash set is still going to be proportional to the input, right? We never get rid of this completely. And this is a little bit of a distinction you have to make between the complexity and the physical space. What you suggested does reduce the physical space needed because we removed it from a value that was 4 bytes per value to 1 byte per value to no values itself. But we're still using a size that scales with the input, and that's something that we want to avoid.
Can you XOR it?
That's actually exactly the solution. So is everyone familiar with what the XOR operator is? Everyone's knows what that is? Okay, perfect. So what are some properties of the XOR that we can actually abuse here? So suppose we have 2 elements, right? If they're the same element and we XOR them, what do we get as the result? Exactly. And now if we XOR something with a 0, what do we get? Itself. Right. And these are 2 really important properties, right? So when we have this 1, 3, 4, 3, 1 pattern, what this actually allows us to do is cancel out things that appear twice. We know that if we XOR the 3 and the 3, right, that results in a 0. If we XOR the 1 and the 1, that results in the 0. And now we just have something that's 0 XOR 4, which just leaves the 4. So now this is a very, it's kind of a cool trick where we actually use the bitwise representation of the numbers in order to sort of isolate the bits of the number that only appears once. So is that clear? I know this is a little bit advanced using the XOR, but does everyone get why we're allowed to do that on this array?
This would ever feasibly come up in an interview.
This problem?
Like, I've never XORed anything in my life.
So yeah, big questions do come up in interviews. Generally, I think the rule of thumb is interview problems are related to the field that you're applying to, right? So if you're going to be working with something that concerns the efficiency of various things, like say you're designing some sort of like GPU accelerators where you want to, what's it called? You want to like levy the bitwise sparsity of calculations. That's going to be somewhere where you might be asked to do a bitwise calculation, right? And yeah, so whether the fact this actually appears on an interview or not, this is straight from LeetCode, so it has appeared in some interviews. Yeah, but it's always cool to have like the bitwise tricks up your sleeve, especially since when you've taken CS33 over here, which is mandatory, you'll be very familiar with exactly like how things are represented. All right, so moving on to the next problem. It's another simple linked list problem, just to sort of get you warmed up with dealing with sort of these edges, arrows, whatever you want to call it, for the graphs and trees workshop next week. So first of all, who's actually seen this problem already?
1, 2.
2.
I think, isn't there like a CS meme?
It
Like this is
might
a
be.
meme,
It could be. No, the meme is invert the binary tree.
That's the guy.
right?
who-
What?
I've always seen it reverse linked.
Yeah, I thought this is like a common.
Yeah. But this is always good to just sort of warm up with.
That was the binary tree. It's like the guy who got mad because like the guy who made something like pretty important, and then he was doing an interview somewhere and he can reverse a binary tree.
Yeah.
Couldn't get fired.
Yeah, that's what happened too. So it seems that you're the only person who hasn't seen this problem before.
Mm,
Do you want to take a crack at exactly how to solve it?
oh, okay.
I think you can, it's also good, since we only have 3 people, it's also good practice to just like talk your thought out, because that's what you're required to do in an interview, or at least expect it. If you're just like, oh, let me think about it, and then don't talk, the recruiter will like you a little bit less. Like you should always walk through your thought process, even if they might not be completely full or like flushed out. Just like always tell them what you're thinking right now. So do that.
So,
Good
so is
practice.
this like a circulating base or just simple?
Yeah, so that's a great clarifying question that you asked. So this is going to be just a normal singly linked list, no circular. So it's going to look something like this, where we have a head, and then we have a tail, and you know it's a tail because it just points to null.
So first we'll create another empty node that is null pointer.
Okay.
Uh,
So just null, and then what would the empty node be? Like, is there a relation between these two?
so what I think is
It's always good to just keep talking through what you're thinking at a point, because
so that means you know method, right?
no, it's perfectly fine, because this is something that happens in interviews. If you see a question and you don't exactly know what to do with it, by talking out your thought process, the interviewer will guide you towards a solution, right? Remember, it's not their job to sort of just look at you and see if you figure it out or not. They'll be helping you get to the answer at the end. So generally, when you're in the interview, you'll explain your thought process. And if the thought process is starting to go in the wrong direction, the interviewer will sort of help you and guide you towards the right answer. They'll ask you some questions to get you to think about the proper like formula to get to the right answer, right? So what's the idea behind making the null and the empty node?
Thinking of like, because we're trying to reverse it, so we're trying to for the last one, last node in the original list to be the first one. And so some will, I'm just going with moon hash wonder, geometry. And connect that with the last node of this part.
So let's see if we can get a different way of looking at what exactly reversing a linked list entails, right? So the current idea that you're going through, right, is you're creating a new one and then replacing the values backwards, sort of, right? Now that's something you totally do, right? And if you end up wanting to do it that way, you'd have to leverage an external data structure, right? The whole point of a linked list is you can only read it in one direction, right? There's no real concept of going backwards in a single linked list. So if you wanted to do it your way, where you sort of save the values and then make a new linked list with inverted values, you'd have to use some sort of intermediary structure, like a list, fill these in with the values, and then use the fact that the list can be read backwards in order to fill it back, right? But now this is using an external data space, right? So let's think about how you actually want to reverse the linked list without using an external condition, right?
Maybe we can like traverse the second to last node and just last node before the node and like set
So that's a good idea, right? What you're
set-
thinking,
set the last node's map to the previous node.
that's perfect. That's actually the idea you're trying to get to, right? at some point, we actually have to reverse these connections, right? So this connection over here, where we have this pointer, we actually want it to go backwards. Now, one problem with the way that you're approaching it is we don't really have a concept of second to last node, right? And why is that? When we're traversing through a linked list, we can't actually tell we're at the end until we hit this null, right? So there's no concept of really knowing second to last, because when we're here at the second to last node, we always see is that there is a node in front of me. Only when we get to the last node do we see, oh, our next pointer is pointing to null, this must be the end, right? So whatever we want to do with any reversal that we're going through, we have to start at the beginning. And only then can we make sure that we hit everything.
I mean, we can traverse it to the second to last node by checking that whether the next and next node, the next of the next node is null.
Okay.
So we can stop there if that condition runs.
Okay. And now what do they want to do here?
So basically, what I'm saying is you have to store the pointers of like the neighboring pointers nodes when you're doing this traversal. Store at least 3 of them. So that you can set the. So for example, you're arriving at the second to last node, and you're going to set the next of the second to last node to the previous one, which is also stored in your loop, and make the next point to yourself.
Yeah, and make this one point to yourself.
Yeah.
Perfect. So that's actually how you want to do it, right? On these three. And how you would translate this to an arbitrary linked list, right? That can be any amount long, is you always keep those 3 stored, right? And all we have to do is when we have these 3 nodes, the second node needs to point to the first, right? And this node over here becomes the new middle, right? So how we would update this is make this pointer move here, this pointer moves here, and now we still have this connection left over, so we move this pointer over here, right? So that's great. You've devised actually how to solve this problem, right? And now an exercise that I would recommend is when you get back to the dorm or whatever, I'd recommend actually going to LeetCode and coding this problem yourself, right? Because there's a lot of value in knowing how to approach the problem and actually put it onto code, right? So we won't be expecting this right now since we're not officially doing any mock interviews, but something to keep in mind is always keep edge cases in your mind. What happens if we just have only null, right? What happens if we have a single one that points to null? All of this stuff you have to account for in your actual coded solution. All right, but great answer. Yeah, sorry for putting you on the spot, but great job.
Yeah, really only 2 officers. Let's go. Let's go.
All right, so now moving on to the slightly more difficult problems, right? So this problem is the product of array except for self. So essentially what you want to do is you want to multiply every single number inside the array and then return whatever the multiple is divided by the current, except you're not allowed to use the division operation.
We saw something magic similar to this.
Yeah, that's a great hint.
Actually, no, this one too. Sorry.
That's no worries. So does anyone have any ideas of, how to go through with this? Remember, it's perfectly fine to start from just the simplest way to do it and then work your way towards a better answer, right? You don't have to get the optimized answer on the first try.
So what I'm thinking is just first we traverse and hierarchical the product of just everything. And store that as an integer or something. And then we'll traverse again, but this time we'll use that product we just calculated and divide it by the element of the index and store the result to a new array.
Yeah, so that's a good idea, except in the problem statement, we're actually constrained to not using the division operation.
Oh,
Right, so that makes it slightly harder. Otherwise, the solution that you gave would be definitely optimal. You just go through everything and then divide everything in the second pass. But we can't do that, unfortunately.
What are your names?
We're Felix.
Kevin.
Felix, Kevin. Okay, Felix, since you've gone over this problem, do you want to talk about your idea?
No. I have to review it. I haven't touched the code for like.
Don't touch your computer on the spot right now. Pretend this is an interview. But yes.
Remember the steps.
I'm so sad.
There's more in the problem that we haven't used.
Yeah.
Well,
Again, you can start from the very beginning.
was that the problem choice? Yeah. More in the problem that we haven't used.
What have we not used?
Or at least like a good clue of where to start, I should say.
So what Suhas is trying to point out here is this line in the middle right here. So the idea is they've told you explicitly that the product of any prefix or suffix of the sum is guaranteed to fit in a 32-bit integer, right? Now what this should point you towards is, oh, if they're telling me that this does fit, maybe there's something I need to do with these two values to get the optimal answer.
What do you mean by prefix?
Okay, perfect. Good question. So what a prefix or a suffix is, right, is if we have an array, let's call it A, B, C, D, E, F, right? And this can be, all of these are integers, right? Let's say that C is our pivot point. Now a prefix of C would be A and B, right? Everything that comes before C, that's a prefix. Now anything that comes after C is a suffix. So in the array, the prefix and the suffix are both the parts of the array that does not contain C. Right? Does that help at all?
Yeah, I understand that. So the prefix is the A and B is
So now something maybe also clear that would clear it up is when we have a product, A times B times C times D times E times F, right? When we want to divide out C, what does this multiplication look like? It looks like A times B times D times E times, right? Now, there's a very natural grouping we can make here. We can group it into a prefix, right, which corresponds here, and a suffix, which corresponds there. All right, so now there's something we can do with the prefix and the suffix, right? Now the question is, how do we get that prefix? How do we get that suffix? So try to think of these as two separate problems, right? Getting the prefix, that's a whole problem by itself. Getting a suffix, that's a whole problem by itself. And once you solve those two problems, you actually know how to get to the final answer. Let's start with the prefix. Does anyone have any idea how to get the prefix product in an array? Yeah, let's look at that same array that has 6 elements. remember again that we need to do this prefix product for every single pivot position. So always a good starting point is we start at the smallest case, right? What is the smallest case? What do we have when we have a prefix of A? Yeah, this is just empty, right? So prefix being empty and us knowing that we have to make a product, we would actually say that the prefix of A is 1. Right now,
Oh, I see. So I kind of see this for like one, like so the max prefix will be basically the previous element times the second element.
exactly. And that's how you want to get
And
that
so you
prefix.
go through this first and goes to suffix again and multiply it.
Exactly. That's how you solve it. So now for people on Zoom or in the recording who didn't hear, what he said is we can actually solve the prefix problem by simply taking the previous value in the prefix array and the previous value in the actual number array and multiplying those together to get the prefix product. So now as we go through, this is going to give us an array of all prefixes. Now a suffix, there is a slight change to how we would want to do it. So how would we want to approach a suffix? Right? Where is the minimal suffix? Which side of the array is it on? Exactly. It's on the right side because we know that a suffix of F is the empty suffix. So now we have to do the same thing that we've done, except we go backwards because we always need to know the suffix of elements moving backwards. And that's where we divide the multiplication. Because now this becomes F, and then EF, and then DEF, and so on. And now that we have the prefix and the suffix, all we have to do here is do an element-wise product. So we know that the total product except for itself is equal to the prefix times the suffix. Right? And that's how you would go about solving this problem. Is everything clear? Does anyone have any questions in Zoom?
What is the type complexity?
Great question. Does anyone want to answer that?
Okay.
Okay. I think just the old.
ON, exactly. And now the reason that is because we take one iteration to go all the way through the prefix product, one iteration to go all the way through the suffix product, and then one iteration to go all the way through there. So we'd have 3n total things, and now we know that that reduces to ON. And now for the last problem of the workshop is going to be the hardest problem of the workshop. So the problem is an LRU cache.
Did you time it so that we could do this question?
So this is quite a tricky problem, and it makes sort of use of a combination of data types that we've already discussed. So again, I've got to ask, has anyone seen this problem before? Have you implemented an LRU cache, or do you just know what an LRU cache is? Okay. So once again, it falls to Kevin. Yeah. So now, since this is such a tricky problem, I'm not actually going to be getting into how to code this, right? Coding will be left as an exercise after.
Homework.
Homework, yeah, exactly. But now the question is, what exactly do we need to provide in an LRU cache, right? So first of all, are you familiar with what a cache is, or what a cache design is?
Cache or check?
Not really. Okay. So the first step is, what exactly is a cache? Right. And now the answer here is, to put into simple terms, a cache is a place where you store data that you think you might need later. Right. So when we have cache and we store in it A, B, C, D with the expectation that instead of having to go to an external memory source, right, we can instead look them up in the cache. So it would operate something like this. Suppose that this sort of server, right, that we're accessing this data from is from somewhere really far away, like Australia. Now, the thing is, if we want to get data piece A, we have to go all the way to Australia and all the way back to access A. Now, the thing is, we don't want to be paying that cost of time to communicate all the way to Australia and back every time we want that data, right? If we're accessing that data, like say 1 million times repetitively, we're going to be paying the cost of an entire trip from Australia and back over and over again, and that's going to be way too much. So what we do is we set up a sort of intermediary server locally. We'll call this Los Angeles. So instead of immediately going back from Australia, we now instead send the data to LA, store the data locally in LA with the expectation that when we get this, if we ever want to know what the value is again, we simply have to just go to Los Angeles, right? So it's a middleman that makes accessing things a lot faster. Now, the thing about accessing things faster is for fast access, you generally have to have a smaller sort of data store, right? With the logic that if you're sifting through a ginormous amount of data, every time you try to access it, it's going to be really slow. So we want to keep a small subset of data that we think we're going to access again. So what this would mean is that this is a finite size, right? We only have so many slots to store variables in, right? Is this all making sense so far?
I just look at like the description. I think it's pretty similar to like a map, but basically you have a capacity.
Exactly. So that's pretty much what a cache is. It is a map where we say, do we have this data? And if we have the data, immediately return it, right? So now what you notice, the similarity with the map is we want to have constant time access and constant time entry, right? We need to be able to query A and immediately get it back. We don't want to search through the entire thing. We need to just know where it is, right? So yeah, it's a hash map with a fixed capacity, right? We can't just keep putting more things in. So yeah.
So basically you need to know what is the least recent measure.
Yes.
And store that. So that every time you try to shoot it and if the capacity is full, you have to get rid of that.
Perfect. And that's exactly what an LRU cache is. LRU is what's called an eviction policy, which says that basically a brief aside into what the logic is we're saying when we try to access a cache, we're trying to get a lot of repeated entries, right? So if you have an element that hasn't been used in a really, really long time, we're thinking that, oh, we probably won't use it again in the near future. So we get rid of it to put something that we just accessed in with the idea that since we just accessed it, we're probably going to access it again a lot. Okay, so now you had a very good point that we need to store what is the least recently used thing, right? There's two parts of this problem. One is super quick access, and the other part is super quick knowledge of where the least recently used element is, right? So do you have any ideas of what we should do as sort of a starting point? How would we store this?
So to get that O1 complexity, I think you use with the hash.
Perfect.
So you kind of need another structure that indicates like when did you lost this one key. I'm thinking of like a stack or something. So I don't know, but basically, if you so you put a new thing, like for example, there are 10 elements inside the hash right now, and if you use get on one of the key, so you kind of like pull out of it from maybe not a stack, maybe a queue or something. Like you pop the one you get and put it back to the top.
Yeah, so that's a brilliant idea. That's exactly what we need to do, right? We need some sort of structure that allow us to queue in entries in the amount of time that we get them, right? So we have some entries, and this is the order in which they were accessed. But then when we access an element, we need to put it to the front, right? So what are the implications of this, right? If we're going to have something like this, for it to work, we need to be able to add to it in constant time. So we'll call that O of 1 append, right? And O of 1 move, I'll call it, right? Where we sort of move as a combination of a delete and an append, right? So can you think of any data structures that we've discussed where we have a constant time of insertion and a constant time of deletion? So the problem with the queue, right, is that the queue only tells us what the last element in the queue is. So when we have something like a priority queue, where we are given sort of the time and it's always ordered in the time, right? First of all, a priority queue isn't fast enough. It doesn't have this O of 1 guarantee. But a normal queue, we also don't have that guarantee of being able to just pick something out of the middle and put it at the end, right? Because what are the operations we do on a queue or a stack? We either push to the top of the stack or pop from the top of the stacks or push to the back of the queue to the top. All right, so I'll give you a little hint here. What we would want is a linked list. And the reason for this is since we have linked lists in order of the pointers, right? How would we delete something from a linked list? All we have to do is make this arrow point to this element, and then bam, this one's deleted, right? How would we insert this to something? All we would need to do is take this arrow, point it somewhere else, make the new element at the end of that arrow, and point that back, right? So now we have the O of 1 append and the O of 1 move, right? So what have we decided so far? We need a hash table, right? That's the only way to identify the element in constant time. And we need some sort of linked list because that's the only way to move around which element was the least recently used. So now, how would we connect the two? How would we make this into the combination of the least recently used cache? Right, it's pretty clear what the values are in the linked list, right? Whatever data value that we're putting in, right, this int value, that must go into linked list entry. Right, does that make sense?
So when we just store the key.
Yeah, there's no need to store the key, right? Because what do we do with the key? We use the key to identify, right? So where should the key be placed then?
Oh. The hash table.
In the hash table, perfect. So the key would go into the key of the hash table. So now there's one thing missing. How do we connect the hash tables to the linked list to make this a functional cache? So let's preface this by
basically restore the linked list in the table.
So that's an idea. If we store the linked list head, what's the problem here, right? The element A might not be the head, right? So if we store the head of the linked list, we have to actually take more time to search for A. And that's not something we want. We want the hash map to immediately give us the value. So if A is in this node, what do we store in the key value store so that the value immediately gives us the value?
Oh, what is this thing is like?
Oh, okay, perfect. So can you explain that real quick? What the purpose is here is to serve data, right? So we're given a capacity, that's the maximum amount of data we can store, right? When we get a key, what are the things we have to do? We have to O of 1 get the value, right? Now this is simple, but there's one more thing we have to do. Since we just accessed it, we need to update the least recently used, right? Think about it this way. If A was the previous least recently used, but then we get A, we now have to take A and put it to the most recently used, right? We actually have to change the time that it was accessed, right? So that's the additional thing that makes it not just a hash map. Now, when we put something in, it's the same thing. We have to have the O of 1 put the value, but we also have this update of the LRU, right? And the reason we don't just use a hash map only is because these two updates can't be easily done in a hash map. The reason for this is if we stored the least recently used information in the hash map with, say, like a timestamp or something, we actually now have to search through every single element in the hash map to figure out which one was actually least recently used or has the oldest timestamp, right? And now that's bad because we no longer have that guarantee of the constant time get. Okay, does that make sense why we're actually using those two constructs? Yeah.
So when you try, get use get function, you basically you store that value you get.
Yeah, so when we have a get, we actually have to put our item to the head of the linked list because the head of the linked list is the one that's the most recently used. So then we know the tail is the least recently used, right? So I'll just give away what the solution is. We actually have to index the linked list node itself. So A should be mapped to node that contains A. Now it's very clear as to why this is, because once we have a node that points to A, we can actually use that pointer directly to insert itself into the head of the linked list. So once we have the node in the hash table, we can do all of those operations of the update from just using pointers. And we know that has to be O of 1. Is that clear?
Yeah.
So again, a lot of the difficulty of this problem is split into two things. It's knowing exactly how to do this, but knowing how to do this is just the first step. You actually have to be able to implement all of this stuff yourself. So you have to build a linked list, right? So you have to give an appropriate like linked list class or whatever if you're doing this in C++. And then you have to integrate it with the hash table. So the hard parts are building a linked list, figuring out how to insert and remove items from that linked list as member functions, and then actually connecting it to the hash table and keeping track of everything, right? So I would highly recommend that after this workshop, you should go and just do this problem. It's quite useful problem if you like really want to make sure you understand how to work with linked lists. But on that note, that is the end of the workshop. So yeah, thank you guys so much for coming. Yeah, it's a little bonus problem. If you really want to do this, then come to office hours and we can talk about this. Very cool problem, but probably even harder than linked lists or the LRU cache one. Anyway, so please go ahead and leave your feedback in the feedback form. So if you have any particular topics that you want to go over, yeah, tell us that in the feedback form. We'll see if we can fit that into the advanced topics section. All right, I'll end the recording now. And if you guys have any last questions, go ahead and ask.